All right, so we're in Journal 13, and we have this problem here, which is very similar to the ones that you guys have seen on the homework. And so when you're doing this problem, oh, by the way, just heads up, my parents are in town, so you might hear their voices in the background. But let's get back to the bell work here. There are two equations, and we want to estimate their solution. So remember, when we're trying to figure out two equation solution, we want to graph them so we can see where they intercept, because their intersection tells us what x value and what y values that they both equal at. And so in this case, I can't graph this just quite yet because I don't know what my slope is, nor do I know what my intercept is. So that's why the first step that we need to do is to get the y by itself. So if I want to get the y by itself with the first equation, then I need to take my first equation here, and it looks like I need to move over the 3x first, the minus 3x first, so I can get the y by itself. So that's what I'm going to do. I'm going to add 3x to both sides because that's the opposite, so that allows me to cancel. And then y comes down. These two, 4 and 3x, are not like terms, so that's when we just bring them down as they are, so 4 plus 3x. And so now we have it in slope-intercept form, so we can go ahead and graph it. So on here, our intercept is 4, so on our y-axis, we're going to plot it at 4. And then our slope here is 3, so that means that our slope is 3 over 1. So we're going to go up 3. It looks like I'm going to go off the grid a little bit, but that's okay. So if we go up 3, we have to go over 1 to the right, so right there. And then I'm going to connect the dots. Now, I said yesterday, graphing is all about estimating the solution. So what we're doing is we need to draw a graph that is as accurate as possible. So I'm going to add more points on here. So to do that, I'm going to go down 3 over to the left. So I'm still using that same slope, but I'm going the opposite direction. So down 3 over to the left. Down 3 over to the left. And then that's as much as I can do for this grid. So you want to try to make your line as straight as possible using your slope, so more points are needed. And then I'm going to get the second equation where the y is by itself. So I need to move that. So I need to maybe subtract the 6x off first. So we'll subtract that off. That cancels. And then negative 2y comes down, negative 8 minus 6x. And so the next thing I need to do is divide by negative 2. But whenever you divide by negative 2, make sure you divide it on both terms on the other side. So this gets divided by negative 2, and so does this one. Well, then this cancels. So now y is by itself, right? Y is by itself. Then negative 8 divided by negative 2 is positive 4. And then negative 6 divided by negative 2 is positive 3, and then we have an x next to there. Hey, wait a minute. Isn't this line the same as this line, right? Whoa. So if these two are the same lines, that means that they are on top of each other. When the lines are on top of each other, that means that the solution here is going to be infinitely many solutions, because if the lines are on top of each other, that means they're going to intersect everywhere. Their x and y's are always going to equal each other no matter where you are on the coordinate system. So one thing for sure is, like, I don't need to graph this line because it would be the exact same line as the one that I did for the first equation. So in this case, whenever the lines you realize are both the same, it is infinitely many solutions because every x and y value will intersect each other. All right, so hopefully that helps you with packet 3, page 1. There's a very similar problem that looks like that for today. So we've learned about graphing to solve for a linear system. So if you are given two equations, we can find where they intercept, so that is our solution that we're trying to find. So that's by graphing. But we also learned that graphing depends a lot on your drawing skill. So, if you mess up on your drawing, you're not going to intercept it really well, or you're not going to find your estimation for your intercept might be wrong. So what we need to do here is to have other methods for solving that might be more accurate. So today I'm going to teach you something called substitution. Okay, so here is some notes about substitution. The substitution method is where you choose one of the equation and then solve for one of the variables. So when you solve for a variable, you can take what it equals and plug it into the other equation so you can solve that x and y value. So remember, the game is to try to get the x and y by itself, to solve for x and y. Okay, so let's start out with our first example problem here. So this example, we're using substitution. So I want you to first look at these two equations and decide which variable is already solved. So you always want to look at your two equations and determine if a variable is already solved, so that way you can plug it in to replace the other equation's variable. Because if this is true, if the variable is already solved, then you could easily skip the first step. If it's not solved, then you have to solve one of them. So in this case, what I notice is that this y is already by itself and y equals 3x. So in this case, I can take this, what y equals, which is 3x, the expression, and plug it into the other equation's y value. Because if y equals 3x, then I can replace that with 3x instead, and then work this out. So notice how right now each of the equations both have a y and an x, and I don't want that when I'm solving, because when I replace this here, so I'm going to plug in 3x into the first equation, and so I would have 3x plus 2x equals 10, right? And so notice that when I replace that variable, there's only one variable to deal with now, which makes it more possible for me to get a variable by itself. So now I'm going to just try to get x by itself. So 3x plus 2x is 5x equals 10. Now I'm going to divide by 5 to get rid of that 5 here. And then x is equal to 2. Okay, so we have our x value. But here's the thing. Remember when we're trying to find when we have two equations and we graph them, we typically look for their interceptions, right? You graph your equations, you look for your intersection, and an intersection is a coordinate with an x and a y. So it's like we have found their intersection, but we only have the x value. We need the y value. So how do we get the y value? Take a moment to think about it. Okay, so what we could do is, because we have two equations, I could just plug 2 into one of the equations, it does not matter which one, so that I can find my y value, right? So I'm going to plug into the second equation because it's shorter. I only have to plug in the 2 here and then work it out. It's just easier to use the second equation, so why not make this hard on myself? So I would have 3 times 2 when I'm plugging my x in. And so now, if I work this out, 3 times 2 is just 6, so y is 6. So you can keep your answer like this, or what you will start to notice how I write my answer key and how I do my test is that it's usually written as a coordinate because it's an intersection. So my x here is 2 and my y here is 6. So I can write that as a coordinate, and because there's only one coordinate here, or one intersection, that means we only have one solution. And that's it, guys. We have just solved for the system of equations, and now we know what x value and what y value make these two equal to each other. Okay, so next do another example here. We're going to try to do 3 examples. All right, so in this example here, what I have is 2 equations. And like I said before, I want you to look at these 2 equations and then determine if the variable is already solved, if one of the variables is already solved, because it makes our life a little bit easier when it's already solved. Okay, so hopefully you guys noticed that both of these equations already has y by itself. So that's really nice, because can't I just take one of them? I'm going to take the bottom one. Doesn't really matter. But can I just take what that y equals and then just plug it into that y like we did before? Right, we can. Because that says that y equals this expression, so I can replace it wherever I see a y. And so in that case, this is really 2x plus 8. And so that would go here. Then there's an equals 5x minus 10. And now notice how we just went from two variables in an equation, right? They both have two variables. But now we are down to just one variable, and that variable is just x's. So now we can get the x by itself. So if we were trying to get the x by itself, let's be strategic here. Maybe moving this 2x to that side. I can subtract 2x. So that side would cancel, and then I would have 8 equals 3x minus 10. And then if I add 10 to both sides, that part cancels, and then I have a 3x equals 18 on this side, because 8 plus 10 gives me 18. If I divide by 3, I can get rid of that 3 on the x. So that cancels, so x is equal to 6. Okay, great. I got my x value, but I'm not done. Remember, we need an x and a y value here. So in this case, I just have that x value. I need to get my y value. So just like last time, we're going to choose which equation to plug in the 6. It doesn't matter which one you choose. Maybe I'll choose the second one because, you know, maybe I prefer to add more than I do to subtract. So I'll just pick the second one. So we have y equals 2x, but x is 6 that I'm plugging in, plus 8. And if I work this out, I would have y equals 12 plus 8. 2 times 6 gives me 12. If I add these two numbers together, I have y equals 20. And I have my y value. So now that I have my y value and my x value, I can put them together as a coordinate and write it as 6, 20. And there's only one intersection here, or one coordinate. So this is only one solution. Sorry for the noise background. So let's get to our third example here. Notice that this time around, I have two equations where x and y's are both on one side. So that means this time around, you guys don't have x or y already solved for you. That means you have to solve for one of the variables of the equation, so that way you can get it by itself first. So this is a little bit more work, but it's definitely not possible. But I want you to start thinking from the three different types, like which one did you feel like was easy to use substitution, and which one did you feel like that was not easy to use substitution? Because this one here definitely puts us a constraint because the variable isn't solved for us. So in this case, this one might not be preferable to use substitution, but the thing is we still can use it. But on Monday, I'll teach you a method that might be easier to handle this situation when it's in standard form, when the x and y's are both on one side. So when we have this here, we have we have equation, I'll call this equation 1 and this one equation 2. So for these equations here, I'm going to try to look at them and see which one might be easier for me to solve for one variable. And it looks like it's number 1, right? Because number 1 here, to get this y by itself, I would just have to move this 5x. And the y doesn't have a number in front of it, so the y just automatically becomes by itself. Whereas this one here, I would have to move over the 3x, and then I would have to move over the 8. It's just be a much more work for me. So instead, I'm just going to take number 1, equation 1. I'm just going to rewrite it down here. And I'm going to try to solve for the y here. So if I solve for the y, maybe move over the 5x. That cancel, y drops down. These two are not like terms, so I just bring them down. And then I have negative 3 plus 5x. And in this case here, now the y is by itself. So I can use what y equals and plug it in for the other equation's y, and then solve for my variable. So if I were to do that, I'm going to take my second equation, 3x minus 8, and then wherever I see a y, I'm going to be plugging in what y equals, which is negative 3 plus 5x. And so this is going to equal 24. So working this out. You might have also noticed that when I'm plugging stuff in, I've been using parentheses, right? And that's just because if I didn't use parentheses, maybe I wouldn't have seen that I had to distribute this -8 to the 3 and to the 5x. So it's always better to use parentheses, so that way you are making sure you're distributing it to everything inside of what you are plugging in. So from here, I would bring down the 3x. -8 times -3 is positive 24. -8 times 5x is -40x equals 24. These two are like terms, so 3 minus 40 is -37. X. And then I have a 24 that comes down, and then I have 24 on the other side. So the x needs to be by itself. Maybe subtract over the 24 first, which makes it 0 on this side, which is kind of nice. And then I have -37 on this side, so I need to divide that off. That cancels. So x is equal to, okay, 0 divided by -37. When 0's on top, that means that this here is going to equal 0. So my x here is equal to 0. So from here, I need to figure out what my y is. So maybe I'll take the first equation and I'll plug in 0 because that y is already by itself. So let's see here. So I'm going to take the first equation again, plug in 0 for x, plus y equals -3. If I work this out, doesn't 0 times any number just become 0, right? So that just becomes 0, so that really just disappears. And then y drops down, and then y equals -3. So my coordinate here is going to be 0, -3, and because I only have one coordinate here, this is one solution. And that's it. Okay, so now that we've tried out a lot of problems here, I want you to try your packet 3, page 2, and see if you can do some of those problems using these examples to help you out. All right, that's it, guys.